function, the logarithmic function, in some business applications. We have already discussed the polynomials in the previous worksheets. And the polynomials, like we said, if we have any positive whole number in the power of x, like when we have x to the power of 99 minus x to the power of 7 plus 3, this is the polynomial where its domain is all real numbers. And we have discussed the radical function, which is the root function. If we have like 2x minus 3 or any function under an even root, the square root, the fourth root, the sixth root, we said that the domain should be positive, and we set the condition that the function inside the root, which will be input to the root, has to be bigger than or equal 0. And then we introduced the rational function, which is a fraction. If we have 1 over x, we said that the domain can't include the 0 because we cannot divide by 0. And then we discussed also the absolute function and its behavior in equation and inequalities. So if we have any equation under the absolute, we know that the domain is all real numbers in addition to the odd roots. So if we have an odd root function, this is the other type of radical of any function. We say that the domain here is all real numbers. So we have the domain all real number for the polynomial, the absolute of a function, and the odd root. This odd root might be the 7th root, the 3rd root, the 5th root of any function. Okay, this is as an example. This is the first category. And then we have the root, the even root, where we set the inside for all what's under the root to be positive, bigger than or equal 0. And finally the rational, where we forbid the division by 0. And now we want to add to these functions the two functions, the exponential and the logarithmic. The exponential function, we have dealt with it before. It's like we say 2 to the power of 3. This is actually an exponential function where we have the base as 2 and 3 is the exponent or the power, and its opposite or its inverse function. After some time of using the exponential function, they needed a function to solve for the exponent, and then the logarithmic came. Let's see the graph or how that the exponential function looks like. Here it looks like that curve is small and getting to increase, hitting the y-axis at y equals 1 at the point 0 and 1. So this function, if we want to evaluate it at 0, it will be f of 0 equals to 1. For that, f of x, which is in general a to the power of x, any constant like 2 to the power of x, 5 to the power of x, any number which is bigger than 1. Bigger than 1 and not equal, just bigger than 1, will have the same graph increasing, which is representing a lot of the graph function in different pharmaceutical applications. So what we need to identify is that function at 0. We know that any number power 0 is equal to 1 except the 0, of course. We might also study the ending behavior of that function as x is increasing without a bound, which we call the limit of x approaching infinity for the any constant to the power of x in exponential function. And in this case, as x is increasing, as you see here, the function will keep increasing. That arrow, the function keeps increasing, and that means that this is equal to infinity. If we took the other side behavior as x is approaching negative infinity, where x is decreasing, getting to decrease on that side, we will find that 2 to the power of x or any exponential function like we described will approach the 0. However, if we evaluated the function at a very small value, the function will not be able, or it will have a corresponding value, a different corresponding value approaching the 0 value. So now we know how the function looks like, the exponential function of any positive whole number as a base, having x as a power or exponent. It will look like this, small and getting to increase, crossing the y-axis at 1, giving the value f of 0 equals to 1, and we knew this before. If that constant that we discussed in the base is set by e, and you remember e, we dealt with it before, it's approximately 2.71 and it's a non-terminating decimal, which is an irrational number. This is why we call it e, the Euclidean constant. We call it e in order to be able and to facilitate dealing with it. So if the base is e, it's called the natural exponential function. We will add that name, the natural exponential function, and we will deal with the properties of the exponential function that you already know from previous years. We know that if we have two exponential functions in multiplication, and if we have them in division, and if we have a power inside and a power outside, and finally if we have a negative exponent. If we have a product of two exponential function, what we do, we can combine both in one exponential with one base, and what do we do to the power? This multiplication is reflected to addition, and if they were in division, this division is reflected to subtraction. And if we have a power inside and a power outside, let's call the outside, for example here, y. So a to the power of x all raised to the power of y is going to be a power x times y. This is the only multiplication case in the power. The negative exponent, we will just imagine it's over 1, right? If we have 2 or 3, we can say it's over 1 if you want to set it in a fraction form, or read it as in a fraction. You will say as if it's over 1. So we will flip this and change the sign of the power. So this flipping that we did will exchange the sign of the power. Now we have this first property, number 2, number 3, and number 4 for that exponential, and these properties work the same for the exponential, the natural one, the natural exponential. So if we have e power x times e power y, and between them there is nothing, which we read it as multiplication, we will add the powers, and so on with the other properties. Let's take the exercise here in worksheet 4. Use the properties of exponents to simplify the following expressions. Let's do this here. Okay, number 1. We have e to the power of 3 times e to the power of 4. So what can we do here? We can rewrite this into one exponential function with one base e, and the multiplication is turned to addition, so it will be e to the power of 7 here. Okay, what about the power inside and outside? Yes, this is the only case where we multiply the inside to the outside. So a to the power of x all raised to the power of y will be a to the power of x times y, which is 12. Here we have a quotient, so we might write these two exponential functions into one and do what to the powers? The divide is translated into subtraction, so we will minus the negative 2, and we know that 3 minus negative 2 is 2 to the power of 5, which we can evaluate later. You might evaluate it, of course, and write the final result. Okay, and then This will be okay. So let me solve the problem. So that's 32. Okay. Here we have two exponents in division and then a power outside. Here we have two ways that we can think about that problem. We might first translate the division and say it's 1e to the power of 5 minus 2. Right? We have combined the e to the power of 5 over e to the power of 2. But we should not forget that all of this was raised to the power of negative 2. So 5 minus 2 is what? 3, and then all raised to the power of negative 2, and this will be e to the power negative 6. One might say another solution. One might say that, no, I want to distribute the power outside to the power inside, and then do the division effect. So I will take e to the power of 5 raised to the power of negative 2, and the power inside and outside is multiplied over e to the power of 2 all to the power of negative 2, which will be negative 4 to the power inside times the power outside. This is we do in property 3. The inside and outside powers are multiplied. And then we apply the division effect, which is negative 10 minus the negative 4, which is negative 10 plus 4, which gives e to the power of negative 6, right? And because this is a negative exponent, we always prefer, or the mathematicians always prefer, to express it in a positive notation. So we will finally write that it's 1 over e to the power of positive 6. The negative exponent is simply flipped, and then the sign turns to positive. So these are the two possible solutions one might think of. Let's move to number e. We have two exponential as well multiplied. We might write them in terms of 1 base pi, and what do we do to the power if they were multiplied? We will directly add the power. Negative 2 plus negative 5 over 2, which is negative 2.5 minus 2. This will be minus 4.5, and that's it. So now we recalled some exponential properties. Let's have a look over the logarithmic function. The logarithmic is the opposite of the exponential. So pay attention here with me. If we have, like we said, y is equal to 2 to the power of x, or we want to know 8, for example. 8 is 2 to the power of what? What would we do? Of course, we needed a function to solve for x, and we need to solve this. What shall we do? We will rewrite it as log. We will use that logarithmic function. The logarithmic function takes the same base as the power. So it's 2 power x. 2 is the base. So the log will take the same base. It has a base as well. And it will take that 8 and output the value of x. It'll give us the x, which is equal to 3. You might use this in your calculator. You will find a button for the logarithmic, and you will be allowed to enter the base and the exponent, or you might transfer it to a different form. So the logarithmic function in general is log a of x, and that's the function that we call it y, or we might call it the f of x, like we do. So this function here, where f of x is the log of any base for x. It takes the input x and the base a. The graph will look the opposite of the exponential. So if you drew here the line y equal x, and we applied the reflection in order to get the opposite function or the inverse function, that point, which is 0 and 1, will turn here into 1 and 0. And this is why the logarithmic of 1 is 0. This a here should be bigger than 1 as well. Like we said here, that condition in the exponential, it's the same here with the logarithmic. And about the natural exponential as well, we have a natural logarithmic where we set a into e, the equilibrium, which is 2.71 blah blah blah. So the logarithmic of base e of the x is equivalent to the len. They recode the function into len or ln in order to facilitate also dealing with it. Whenever we see the ln, we know that it's a logarithmic function and the base is kept to e. And it is called the natural logarithmic function, which we'll be mainly dealing with. So our function here is the natural logarithmic, which is the ln of x. We will be able to use it beside the exponential like we will see, but let's have a look over some of the properties of the logarithmic or the natural logarithmic like we did with the exponential. And as you can see here in that graph, they were both drawn in the same coordinates to show us that they are opposite in operation, and we will have another look over that part again when we start solving the equations that includes both of them. Now let's have a look over the logarithmic properties. If we have the ln or the logarithmic of a product, and if we have the ln or the logarithmic of quotient, and finally if we have the logarithmic of an exponent, x raised to the power of n. How can we deal with such situations? If we have the ln or the logarithmic of two operands multiplication, we can distribute the len into both of them to evaluate len x alone and len y. The same if they were in division. We can get len x alone and then len y. And here as well, we can get the len x alone. Okay, what about these other parts? Here we will say that this product will be transferred into addition here. This quotient will be transferred into subtraction. And that power will go as a quotient. And this will be property 1, property 2, and property 3. These are the only three properties. So whenever we have an addition or subtraction between two terms inside the len, we will not distribute the len. We distribute the len only if inside it there is a product or a division or a power, like we see here. Okay, let's keep these properties with us, taking them down here in order to be able to have them in the same screen with the exercises. Our exercise 2, use the properties of the logarithms to rewrite each expression as sum, difference, or multiple of the logarithms. Here the first one, number 1 or number A, we have products here, so we can distribute the len over these terms, right? So it will be equal to len x alone, and then len y alone, and len z alone. And then what do we put in between them? Yes, addition. The product is translated into addition. What about number B here? Number B, we have a square root, the len of the square root, and we know that the square root of x is x to the power of 1/2. Therefore, we might rewrite this first before applying the property. In order to fit to one of the three above properties, rewrite the square root as power of 1/2. And then we might use the property number 3. taking the half as a coefficient, and then the len, and we will leave the x squared plus 1 as it is. Can we factorize the x squared plus 1? No. Can we distribute the len over x squared and 1 to commute len x squared alone and len 1 alone? Of course not, because there is an addition here. We can do this distribution only in multiplication and division, like here in property 1 and 2. But here, now that's the simplest form that we have reached using the property. Okay, let's move to number C, part C. Here we have things in product and other product in the denominator. So we might let the len of x to be commuted alone, and then the len of the y, the len of the t, and the len finally of the z. What about the signs? Here, what's above in the numerator will be kept as positive. So we have len of x times y will be len x plus len y. Of course, we might need to add an addition before the len x, but there is nothing, no term is lying before it, so we don't need to add addition. We know when there is nothing before it, then it is a plus by default. Now we have two terms in the denominator. It's either you make a big minus and open a bracket of addition to apply the product, or you say it's as if it's divided t divided z, so both will take the negative sign. One might say again, if you didn't notice, that it's len x plus len y, and then a big minus and take inside the len t plus len finally z, right? Because both are in the denominator, so we can, yes, add because we have a product, but with the minus before, which later can be distributed to fit into what we have written here at the beginning. If you have noticed it at once, you just write it like that. Okay, now let's move to the next z. We have here x power 3 times x plus 1. So we might commute len x power 3 first, and then len x plus 1. And we have to include this bracket because we want to keep reading it len x plus 1. If we didn't put the bracket, you might read it later len x plus 1 as if it's len x only and then plus 1. So if you want it len to be for x plus 1 in general, we have to put the bracket like this. Also, a common mistake that I noticed, we are not reading the ln of x as a product. So it's not ln times x. It's not like this. It's like the square root of x. Can you say that the square root is multiplied to the x? No, it's the square root of x. The same as the len or the ln. It's the ln of x. It's a function applied over the x. Okay, like we say, if we noticed in the graph that we discussed above, that at x equal 1, that function is 0. So we might say that the len of 1 in the calculator, if you use that button in the calculator, you will find it. Len 1 is equal to 0. If you move further here to len 2, it will be equal to a value. Len 3 equal to a value. Like you say 2 power 1, 2 power 2 is 4, 2 power 3, 8, 2 power, and so on. It's a function. And also you may notice that it works for the numbers less than 1, but up till the 0. It doesn't work at the 0. So if you take the limit of that function, which is the ln of x, as x approaching the 0, what will happen? The limit will tell us that the function keeps decreasing with no limit. So it's equal to negative infinity. But the ln of 0 is undefined. The function is not able to define the corresponding y at x equals 0 because the function keeps decreasing with no bound, so it's unable to trace it. There is no corresponding y for x equals 0, but the limit can say as we approach x equals 0, the function approach the negative infinity, which means that the limit does not exist actually, but it keeps decreasing with no limit. Let's go back here to the properties and our exercise. So here we have divided the len and distributed it to the x power 3 and then 3x plus 1. And of course, because there is a product here, we will separate them with the addition. If there is anything left we can do, yes, property number 3, which looks here, we might put the power of the function inside, outside to be 3 len x plus the len of x plus 1. And that's the simplest form. Again, we cannot distribute the len to the x and 1 because between them there is an addition. We do that distribution if between them there is multiplication or division. Now let's work out the e part. Here it's ln and then a function, and that function is given the fifth root. That's the fifth root. Because we know that the square root is the equivalent to x to the power of half, the fifth root also, we know that it's equivalent to x to the power 1 over 5, right? So we might rewrite that form is equal to len and all raised to the power of 1 over 5. Of what? We will keep the rest, all the rest as they are, x plus 3 all raised to the power of 9 over x minus 5. And then using property number 3, we might take that power as an exponent, right? And also leave the rest as they are till now. Now we were working in the power. We transferred the root into its exponential fraction form, and then we used the property which take it as a coefficient. When we have, for example, len x to the power of a, it's equivalent to a of len of the x. These properties were very beneficial in the old days, because before the calculators, because they had huge tables for the logarithmic of different values, the log of 2, the log of 3, the log of 4. They can look up that values in the table, so it was easier for them to get log 2 instead of log 2 times 3. I'm giving, of course, a simple example to make it short to your mind. If we have the len of 2 times 3, instead of saying this or evaluating this, we have a table which gives us the value of len 2 and a value of len 3. So we might distribute the len over the 2 and 3 and add them. This would be much easier. So these properties are working till nowadays. Now we have the 1 over 5 len of this bulk of expressions. Let's simplify it with the properties 1 over 5 and then distribute the len in order to calculate len x power 3 alone, and then len x plus 3 all to the power of 9 alone, and then len x minus 5 alone. Now we need to add the signs according to the position. X power 3 is in the numerator, x power 9, the bracket of x of power 9 is in the numerator, so both will take the addition. We don't need to indicate it here, and here we indicate it. And x minus 5 will take minus because it's in the denominator. Is there something left? Someone will tell me, yes, you have just said that property, so let's use it. It will be 1 over 5 times, drop the 3 to be len x, and then plus, drop the 9 to have len x plus 3, and then minus, we don't have a power here, so we'll keep it len x minus 5, and that's it. Now, can we do any simplification further? No, that's the simplest form. Very good. Let's move to exercise B. Here we need to use the properties of the logarithms to rewrite the expression as the logarithms of the logarithm of a single quantity, as if what we were doing was an expansion, and what we are about to do is what is the condensing, right? Okay, so we have here this number beside the len and two len functions separated with a minus. So what do we do first? We need to be left with the minus in order to say it's the len x minus len, for example, y, which can be rewritten as len x over y, right? This is what we want. But with the coefficients, we cannot directly do this. We can use the other one property, which says len x to the power of n is equivalent to n len x, right? Okay, so let's do this here. We will say that's equivalent to len x minus 3 raised to the power of 2 and len x plus 5 raised to the power of what? 3, and keep the minus. And then we will combine them into one len as x minus 3 squared over x plus 5 power what? Power 3. And all of these are input to the len, right? One might have taken the negative 3, all of the negative 3 as a power. This is fine, and in that case, this will be a plus, not minus. This is another solution if someone thought about it. It will be a plus, so you will turn it to a product, and then you will have this bracket with a power negative. So you will move it down and flip it to have a positive power using the exponential property. So no matter, you will reach the same solution, but this is more forward. Here is the same, so let's also return the powers, and then plus len x minus 4 and to the power 3 over 2. Okay, between them there is an addition, so we might rewrite them into one len and do what? And put them as a product, right? And that's it. Now we have rewrite it as one logarithmic expression of a single quantity. Very good. Let's now move to the solving exercise 4, where we will need to solve an equation that includes an x. We will be solving for x. Here we'll solve for x. Equations that include the exponential and the logarithm. We have solved before equations that include the absolute. Do you remember when we have the absolute equals 3? We said that the solution is either x equals 3 or x equals negative 3. Another example, when we had, for example, 3x minus 5 equals 2. This is one equation in one unknown x. We first take the negative 5 to the other side with the opposite sign. So it will be 3x equals what? 7. And then we get rid of the 3 from both sides in order to isolate the x, or solve or subject for x, like you know, and we will get x as 7 over 3. So this is what we were doing before, solving for x. Equations that included absolute and addition and multiplication, and also if we have like the square root of x, also if we know that it's equal to 2, we were able to solve such a problem by doing what? We squared both sides. We know that the square root is power of half, so we squared both sides, and in that case we will be left with the x, right, equals to 2 power 2, which is 4. Keeping in mind that we know that the square root of x squared is equal to x, while the root of the x squared gives the positive and negative x, which is the absolute, and we have discussed this before. These types of equations we were able to solve before. Let's add some other types to them. Here we have in part A, we have 5 times e to the power of x equals 10. We need to solve that equation, and solve an equation with an x means that we want to know what's the value of x. Like we did in example number 2 here. We got rid of the negative 5 first and then the 3. We will divide here by 5 first in order to go from the left side, and the right side will be 10 divides 5, which is 2. Now we have e to the power of x equal 2. Like when we had the square root of x equal 2 here, we did the opposite. So we said that square root of x equal 2 means that x is equal to 4. Here, e to the power of x equal 2 means directly that x is equal to ln 2. Okay, what you did. Let's do it in detail. But this is generally what we will do. You can just do it direct like I did now. What we did here is that we applied the ln to the e to the power of x and then the ln to 2. So we applied the ln to both sides. What will happen to ln and e? We said that they are opposite in operation, like time and division exactly. If you take the x and multiply it with 2, it will be what? 2x. If after that you took the 2x and divided by 2, you will return the same what? Yes, x will return. Here exactly what happened. If you had an x and you input it to the exponential function, let's say to be more clear, x equal to, the output will be e to the power of 2 because we substituted x by 2. Now, if we took the e to the power of 2, which is the output, you can calculate this with the calculator, it's a fraction or a decimal number, and input it to the ln of x, to the function of ln x. I want to write it more clear because I want you to take care that e takes into the power while ln takes as an argument. Okay, so here what you will get out again is the 2. Because what happened, we took the x, which is e to the power of 2, and put it to the ln. The e and ln are opposite in operation, like exactly the time and divide. So they both cancel each other and the 2 return. So this is what will happen, and what we will do dealing with both of them. This is how they will help us in solving more number of equations. What we're having here is only a graph. Okay, so this is what happens. The ln will move with the e and take care that the x remains. Okay, it remains and it's equal to ln of 2. If you calculated ln 2, I will open it here in the Google. Even you might just open it in the Google because I want to show you ln 2 is what? Is that value. Okay, so it's that decimal value 0.69, and you will always deal with the value with the decimal up to 2 decimal places is fair enough. So it's 0.69. The ln 2 is a value. Okay, so instead of writing it in a decimal form, we might leave it as ln 2. Okay, let's solve now part B. Let's solve it here. It's 3 times ln x equals 6. Okay, now there is nothing between the 3 and the ln x. Right? So we know that this is a multiplication and that is an input. It's not ln times x. Again, please, it's not ln times x. So now, what we will do, we will think exactly as if we're having 3 times something we don't know equals 6. What do we do in this situation? We just get rid of the 3. right? And this is what we will do here. Get rid of the 3. They will go together, and we will be left with the len x equals 6 divided 3, which is 2. Okay, now the len, we want to take len to the other side, so it will go like what? Yes, I hear you saying e. It will be e. Tell me in details what happened. Let me tell you in details what happened. Now, because as we divided 3 on both sides, we took here e of both sides, and e take in the power. The input of e is raised to its power directly. This is its nature. This is how it behaves. Okay, so we took e to the power of len x and e to the power of 2. What happens to e with len? They both cancel and the x drop, equal to e to the power of 2. And this is the value. Let's see e to the power of 2. If you here wrote e to the power of 2, just 2, I want to show you this. What I wrote here is e to the power of 2. This is that value, 7.3. Okay, so this is what the e, 7.38, or we might say 7.39 to round it up. So that's it. Okay, so e to the power of 2 is a decimal number. I just want to convince you with that. This is only a note. Okay, let's move to part C. And part C says that 10 over 1 plus 4 times e to the power negative that decimal times x is equal to 2.5. What can happen here? Once we see a fraction, we want to get rid of the fraction, right? If you have, for example, x over 2 equals 4, what do? Without thinking, you multiply by 2 to get rid of the fraction, as if you did the 4 over 1 and you apply the cross product. So it will give x equals 8, right? So this is what we want to do here. We want to imagine 2.5 as if it's over 1 and do the cross multiplication. Let's do it here. 10 times 1, that's 10, equal 2.5 times 1 plus 4 times e to the power of that power. Now it's an equation in one line, in one unknown, which is x, and our eyes is always on the x. This is what we want to isolate. We want to know that x is equals to what? This is our goal. Let's get rid of everything beside it. The first thing we will get rid of is the 2.5, right? And then that one, yes. And then we will divide by 4. And we will apply the len to get rid of the e. And finally we will divide by the negative 0.1 because it will be dropped after we get rid of the e. Let's do this in detail. Now, the first thing, we want to get rid of the 2.5. Let's divide by 2.5. It will be 10 divided by 2.5 equals. The 2.5 here will go with the other 2.5, so it will be 1 plus 4 and the rest. So here, what you did, I divide by 2.5 here and divide all of this by the 2.5, which was cancelled or simplified out, and now we have the bracket and the other number. What shall we do next? This 2.5 is 5 over 2, so it will be 4. 5 over 2, so it's 20 divided 5, which is 4. And we have here 1 plus 4 e to the power negative 0.01x. So it's much more simpler now. Now we will get rid of the 2. We will move to part 2. It's no sign before it, so it means it's plus 1. So we will subtract 1 to get rid of that 1. As if here we added the minus 1 to the rest of the equation, and here I added the plus which was here, right? Now minus 1 goes with the plus 1 and we will be left with 4 to the power of that power. Now we will do what? The fourth thing we mentioned, we will divide by 4, because here 4 is times that, so we do the opposite that we were used to, and we will have e to the power of negative 0.01x equals to 3 over 4, which is 0.75. What's left? Now we have reached the e. Now we are left with the e. And we know if it's e to that power equals this number, this means that that power is equal to the ln of the other side, because that's exactly the opposite. In details, what happens, please? You apply the ln here and you applied the ln here. The ln of 0.75 is dropped as it is. The ln of that e to that power, the ln and the e cancels and that power drops. And then finally, you might pause if you want and think about it for a while. Now we need to divide by the negative 0.01 in order to solve finally for x. And we will have x as ln 0.75 divided by the negative 0.01. That's the ln of a decimal, which will be negative. So I will take it ln 0.75. I will write it here. Ln of 0.75. That's it. Divided by the negative 0.01. This will be that number, 28.76. Let's round it up to 28.777. So it's 28.77. That's the value of x that we were seeking. Very good. Let's take the next exercise. What about number D? I picked this. You can do it now. You have e to the power of ln x equals 4. What happens to the e and ln? Yes, they cancel and the x drop equal 4. That's it. X is equal 4. Okay, here we have ln x plus 1. Let's take a plus 1 to the other side to be 6. It will move to the other side with minus 1, right? With the opposite sign. Ln x equals 6. This means that x is equal to e to the power of 6, right? That's it. We will just leave it like this. It's a positive exponent, so we will leave it. You might write it in a decimal form if you like, but this will be an extra step. E to the power of 6 is very good. It's an accepted solution. What we did here is that we applied in details again the e to each, and the e takes in the power. E to the power ln x equals e to the power of 6. The e and ln does what? Cancels and the x drops. So it's x equals e to the power of 6. What about that one here? It's x to the power of negative 2. Whenever we see a negative exponent, we imagine it's over 1 and we directly flip it to write it in a positive exponent and express it in a positive exponent. The other one, keep it as it is. If you thought about that right side and put that in the calculator, you will find it's 2 divided by e to the power of 2. That e is what? It's nothing except 2.7. It's a number. So as if it's like this. All of this is a number, but it's written in an enhanced, decent way. That's it. Instead of writing it in a decimal form like we said in tutorial 1, that writing it in a fraction would make it an exact form to avoid the accumulation of errors. So it's written in a decent form, and that's it. So it's a number. What we want to solve for here is the x. If you have x in the denominator, so you directly think of dealing with the fraction by cross multiplying, and hence you'll have 2 times x squared, which is 2x squared, equals 1 times e squared, which is e squared. And therefore, we want x squared alone. What do you do here? You divide by 2 both sides in order to cancel that 2 together, and you will be left with e to the power of 2 over 2. That's great. And if x squared is that value, this means that x is the square root of that side. Right? What we did here is we applied the root on both sides. The square and the root cancels, the x's dropped. Right? And the root keeps in the other side. And here we go. Let's move to number G. E to the power of negative again. Oh, it's as if it's over 1. And then 1 over e. Now it's to the power of positive 1 over x. Equal to the square root of e. Square root of e doesn't make any problem to me. It's as if it's 2.7 blah 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 raised to the root. It's no problem. Okay. Now we need to solve it, and we have the x in a fraction, so we imagine this over 1 and apply the cross product. So we have 1 equal root e, which is a number, times e to the power of 1x. This looks like 1 equals a number, so it's any number like 3, e to the power 1 over x. What would you do to the 3 in that case? You will say, I will divide by 3 in order to cancel it from here and have the 1 over 3 equal to the e to the power 1 over x. Please do the same here because it's a number as well. Root 7, it's a number. So we will divide by root e both sides in order to cancel it from here, and we will have then e to the power of 1 over x equals 1 over square root e. Very well. It's e to the power and we have an x. No matter it's an x or 1 over x, now it's not our point. We need to drop that 1 over x or that power because it includes the x. So we need to drop it. Which means, in other words, we need to get rid of the e. And get rid of the e means we have to apply what? The ln. E power that equals this means directly that that power is equal to ln the other side, right? And then simply, if 1 over x is equal to this, then x is equals what? 1 over ln 1 over root 1 over ln of that thing. We make the cross multiplication also, or we replace these two terms. X goes here and the ln of that thing goes there. And you might calculate this in decimal form and write its equivalent decimal. So I might go to the Google here. But here it would be 1 over ln square root of e. It's 1 over ln, and inside the ln it's 1 over the square root of e. What's the value? Oh, it's negative 2. Only negative 2? It's only negative 2. That's the value of x. Very good. So first we change the negative power to positive. This is number 1. And then we cross multiply and get rid of the coefficients And then here we got rid of the e by solving it for len, taking len of both sides, and then directly we flipped these two terms and taken as x equals 1 over that thing. Very good. Here we need to move to the other part of that worksheet of the exponential application, business applications on exponential function. This compound interest, we know that the interest or evaluating and commuting the interest can happen in two different ways. So we might compound the interest in n times, and in that case we will use that formula in calculating it that you have it given here, or it will be compounded continuously with that formula. So here now we have moved from different, we didn't need it because we're dealing with the natural exponential and natural logarithmic. We have the ln of e to the x and the e to the ln of x both here. In both situations the ln and e cancel, and we've reached the compound n times interest that's added compoundly here, and if it's compounded continuously we use the natural exponential form. So let's read that exercise here. Complete the table to determine the balance A for P dollars invested at rate R for T years compounded n times. Once it's say compounded n times, it means that we will use the compounded the compounded n times per year. We will use directly the first formula. So here, let me open the solution. Yes. So here what shall we do? We have the P is given as 1000 and the R is given as 3%. Of course we transfer it to a value. This percent is divided by 100 before using it, so it turns to 0.03, and the T is 10 years. Using that formula, we directly substitute the P value, which is 1000, 1 plus R, which is 0.03 or 3 over 100, over the N, which is indicated in the table here. Once it's 1 here at the first, so it's over N to the power of N, which is 1 times T, which is given here in years as 10. Calculating that value in the calculator, you will find the corresponding A, or that balance would be at the end. And then do the same for N equals 2, 4, 12, and 365. The 1, when the N is 1, it means that the interest is added once, yearly. It's added yearly, because the time here is always given in years. If N is equal to 2, so it's half yearly, every 6 months. The interest is added. It might tell you in the problem that the interest is added 2 times per year or half yearly. Then the problem tells you in an indirect way that N is equal to 2. If it says quarterly, then it's equal to 4. If it says monthly, then it's equal to 12. If it says daily, then it's 365. The daily is the 365. And every time you just substitute the N with the given N and calculate the final balance after the interest is added, however, in different rates, in different compounded times. The rate is fixed by 3%. I mean in different amounts. In the continuous, we use the other formula which we had here for the exponential, the same P but times e to the power of RT. So directly substitute we have here P, which is 1000, and e to the power of r, which is kept constant, times the time, which is given as 10. All the P, R, and T are givens. The e is found in the calculator, which is the exponential function, and then you calculate the corresponding amount that you have at the end. This note here is only for your interpretation. Where n is approaching infinity, this means that it's a continuous compounded. Continuous compounded, not partial, where there is a specific n to substitute. If it's compounded continuously, not partial, like the parts above here, then it's turned into that expression, which we will directly use. Here, let's take that exercise, okay, and then discuss it together in detail. So an investor is purchasing a 12-year certificate, so it means that the T is equal to 12. Of deposits that pays an annual percentage rate of 8%. The annual percentage rate, it means that the R is 8%, and the percent is directly divided by 100, which turns into 0.08 in order to be ready to deal with it. Compounded monthly. Monthly means each month. So as if it's telling us that n is equal to 12 because it's compounded monthly. How much should the person invest in order to obtain? How much should we invest? Is it the A that we will have the amount at the end after doing some deposit, or a starting amount and then 1 plus r over n to the power of nt? That's the formula. So that's the starting amount or the deposit, or simply the deposit, and that's the final amount after the investment. Okay, so we need here to know how much should the person invest in the beginning in order to obtain a balance of that. So we need to find that at maturity at the end. So of course it's obvious that that is the A amount. So direct substituting here, we have A as 15,000 is equal to P, which we are required to find, and then 1 plus R, which is given as 0.08, over N, which is given as 12 in an indirect way when it says compounded monthly, and again, which is 12 times the T, which is given as 12 years. Now we can solve this for P, calculate that number, and then 15,000 divided that other number, it will give you that B is equal to the 5,761.72. Then you will be left with that amount as deposit. This amount should be deposit in order to have that balance at the maturity at the end. Okay, let's move to the next exercise. Exercise 7. Steven deposits $20,000 in an account for 10 years. Compare the balance for each situation. So we need to compare for each situation. The interest rate is 9%. So it seems that the interest rate is constant for all of the situations, and what is different is the amount of compound. So here, the deposit amount that he deposited at the end, it seems that it's not the amount that he's going to have at the end, right? It's the deposited amount, so it's the P, which is the $20,000. Okay. In an account for 10 years, so the time is given in years and ready to use. If it's in months or any other terms, we have to transfer it to years. Compare the balance for each situation. The situation A, the interest rate is equal to 9%, where we directly write it as 0.09. Compounded yearly, and yearly means that n is equal to 1. It will be added once per year. And quarterly means that n is equal to 4, and compounded monthly is 12, and the continuously compound, we will just use the other formula, which is p times e to the power of rt without n. So the n goes, and because here we have taken n is approaching infinity, and this is the formula equivalent which we will be using. So directly we will take these values and apply. Let's do it with part A. The required here is the balance at the end, which is the A, is equal to P times 1 plus R over N to the power of NT. Let's direct substitute P by 20,000, and then 1 plus the R, which is 0.09, over N, which is in part A given as 1, power N, which is 1 times the T, which is 10, and this will give us the value. Let's read it here. The 47,347.2. So this will be the final amount. And we apply the same with changing the n amount in every part, like we do here. Change just the n into 4 in the quarterly, and then into 12 in the monthly, and the continuous one in the E. Let me take the final result and do that continuous part as well. So here we will do B and C like we did in A, and for D we have A is equal to P times e to the power of RT, where P is given by 20,000 and E times R, which is given 0.09, times the T, which is 10. We didn't use any N here, and therefore it will give that amount. Right? Okay. Let's move to the next exercise. How much should be deposited in an account paying 7.2? How much should be deposited? Let's think about this for a moment. How much should be deposited? It means that we need to know how much to deposit. Right? So it's not the final amount, it's the P that's required here. How much should be deposited? Oh, that's the P. In an account paying 7.2%, it seems that that's the interest, which will be 7.2 over the 100, so it will be 0.072. Interest compounded monthly, and monthly means that n is equal to 12. In order to have a balance of that balance, 3 years, so the time is 3 years, and that balance is going to be left at the end from now. I think now everything is complete, right? I will just write the formula. You will have it in the formula sheet. You have to copy it before using it in order not to miss anything. And then we have A is given, so I will substitute that value. The P is the unknown, R is well known, all the others should be known. The N is 12 times T, which is 3, and calculating that for P, so P will be equal to that number divided by that amount after you calculate it in the calculator. and we can read the final answer here from the solution to be 12,500 in approximation. So it's approximated to that amount. Right? So good. Let's move to exercise 9. It looks like the linear model problem that we had in the previous worksheet. Okay, in 2009, the population of virus C in California was that amount. So we have a population that is read as 1034. That was in 2009. Very good. In 2013, the population became of that virus 1711. Write an exponential graph function of the form, and the form is given. Here it's the general form of the exponential function. If you have y equals a times p to the power of x, a is the initial value, or we call it the initial value because at x equals 0, the p power 0 will be 1. So if x is equal to 0, y will be equal to a. That's why they call it the initial value. And then x is the amount that's added, or it's the rate that is added. Okay, we need to use that function that could be used to model y, the population of the virus. So it says that p is equal to y. We can call it y1 and y2 to differentiate between them. So that's p1 and p2. We need to model it using y. In terms of x, the number of years since 2009. So we're starting from 2009. We can say that at that situation, the x1, which is corresponding to y1, because since that year, so that's the starting time, we might use it as 0. And then here in x2, how many years from 2009 to 2013? 4 years. So x2 is 0 plus 4, which is 4. Now we have 2 points where we can use to apply to that model in order to get it, like we did before in the linear model, which was y equal mx plus c. We were requested to find the value of the slope and the y-intercept, right? And have, for example, y equal negative 3x plus 4. Here as well, we need to replace the a and the b. Let's replace the a and the b, substituting with the 2 given points. So when y is 1034, x was 0. And anything power 0 is 1, so that's directly a. Use point 2 with the y 1711 equals, now the a is known as 1034 times p to the power of what? Of 4, because that's the corresponding x. I'm replacing here y2 equals a, which we know it now, times p with the x2. Right? Now we have only one unknown, which is p. First divide 1711 by 1034. 1711 so p power 4 is 1.65, which is the 1711 divided by 1034. This is what we did. And if b power 4 is equal to this, so b alone is equal to the 4th root of 1.65. And you can just directly calculate it and get its exact value. Okay, I'll calculate the 4th root and then write the final result in its decimal form. Okay. Exercise 10. The number of cells double after each process of cell division. We have the number of cells that doubles. Doubles means what? Times 2 after each process of cell division. So for every process, the number doubles every 2 hours. So every 2 hours, we can say it's per 2 hours. If there are 120 bacteria initially, how many bacteria will be there after 1.5 days? Of course, here we might use that model, the exponential model. It will be given with us, and initially we have 120 bacteria. So it means that at x equals 0, the bacteria was equal to 120. And we can reflect this, that the 120 is equal to A, because when B is equal to, let's write it 0 directly, power 0, it will be this A is equal to 120. How many bacteria will be there after 1.5 days? After 1.5 days, we want to know the amount of Y after X is given by 1.5 days. Okay, so it's 1.5 days, and it was said that the number of cells doubles every 2 hours. So what's the amount? It seems that this is not the direct X, right? We need that duration. To calculate that duration, that will help us to find from that duration the corresponding. So let's say that every 2 hours, the 1 day includes 24 hours, right? How many 2 hours do we have here? We have 12 2 hours, right? And the half day, that includes 12 hours. How many 2 hours in the 12 hours? 2 hours. Right? Now in total, we have how many 2 hours? We have 18 2 hours. And this means that the X needed here is the 18. Okay, so directly we will substitute this, and we will say that Y is equal to 120 and the B power the X, which is 18, and here we know that. Okay, so how can we look for the B? What is here raised to the power of 18? We will repeat 18 times the 2 hours, right? So here we might say that Y is 120 with the 18 doubling. So we directly calculate this amount to get the number required for bacteria. 120 times 2 to the power of 18, which is 120 times 2 to the power of 18, which is that big amount. So here is the required amount at the end. Okay, let's copy the number 31457. Okay, so it's that amount. Yes, that big amount. That will be the number of bacteria after 1.5 days of splitting, of doubling, for 1.5 days, starting with, so that's the starting, the initial amount, and this was the doubling for duration or for time of 18.